So this is a continuation of section 2E of focus 2, and we'll be looking at adiabatic changes. So in the previous video we looked at changes in temperature, and now we're going to be investigating changes in pressure of the system under adiabatic conditions. Right? So we're deriving the relationship between pressure and volume for, in this case, a reversible adiabatic expansion. And so we've discussed this several times, that a reversible process is technically impossible because it requires infinite time, but it gives us it basically simplifies our math so that if we do run an experiment, we know we need to approximate reversible conditions. And so a reversible condition just means the system as it expands is constantly in equilibrium with its surroundings, right? So if there's work being done by changing pressure, that means the pressure on the system must be equal to the pressure of the surroundings at all times, right? And so that's the idea of reversible expansion. So what we need to do is we're going to start with a couple of equations, right? So what we're going to try to derive is this relationship between pressure and volume under these conditions. So let's start with a couple of equations, right? So the ideal gas law is going to describe the behavior of a perfect gas, right, before and after any process. So now we're under two constraints, right? Reversibility, three constraints: reversibility, adiabatic, and also a perfect gas. And we're also going to make the reasonable assumption that we're only dealing with a gas that is not changing chemical composition, so it means it remains the same chemical, so no chemical reactions, and we're not changing the amount of moles in the system. So what we can do is write an equation, the ideal gas law, for both the initial values and then the final values, right? Where n and r are going to be constant. Because n and r are constant, that means we can rearrange the equation so the constants are on one side of the equation with all of our other variables that will change on the right-hand side, and we can do the same for our final values. So what we see here is that n and r are constant in both cases, so we can set both of these equations equal to each other. And that's what we see here. So pi vi over ti equals pf vf over tf, right? This is basically Gen Chem 1. We've all seen this before, but rearrangement. We end up with this equation, and now we have a ratio between vi and vf and ti and tf, right? So what we can do here is reach back to what we did in the last video, and we derive that equation of the temperature change of an adiabatic expansion, right? Or specifically a reversible adiabatic expansion. So what we have here is the equation that we derived in our last video lecture. So let's rearrange this so what we can do is end up with this in such a form that we can substitute it back into this equation here. So what I've done here is taken our basic equation for the reversible adiabatic expansion of a gas at constant with changing temperature, right? Rearrange that, so now we have Ti over Tf equals this. Well, there's my Ti over Tf, so I can substitute this part of the equation back into my ideal gas law rearrangement and end up with this here, right? And again, 1 over c just means taking the cth root of that ratio of the volumes. So we're just going to tidy this up a little bit. All I did is the exact same equation. I just pulled this ratio of Vi over Vf into its own parentheses, and I specifically put a 1 up here. Usually you wouldn't do that. This is just to illustrate the math that we'll be doing in the next steps, right? So if we divide both sides by whatever's on the right, we'll end up with this here. So you notice what we divided, we flipped our ratio. Instead of Vf over Vi, it's now Vi over Vf. Still raised to the 1 over cth power, or the cth root of that ratio, will be equal to 1. So what we'll do is we're going to combine like terms. So here's our like terms. There's our ratio of Vi over Vf, Vi over Vf. We can add these two, we're multiplying them together, but exponent rules means we're going to add these two together. And now you can see why I specifically explicitly put down the 1. So I have 1 over c plus 1 for our ratio, and we've simplified and tidied up our terms a little bit, so it's a little easier to see and deal with, right? So what we're going to need to do now is, remember, C equals the molar heat capacity at constant volume over R. That was derived in the last video. So what we're going to do now is basically play only with the exponents until we can get it into something that's a little bit more usable than just the term C. So we're going to expand our C term, and we've already defined C as this. And then our exponent up here is 1 over C plus 1. And so that's what we're looking at here, 1 over C plus 1. We can convert 1 to C over C. It's the same thing, but now we have a common denominator, so we can add these two fractions together to get 1 over C plus, 1 plus C over C. And now we can substitute in what C equals. So now it's 1 plus, so it's a little, I did some cleaning up here, but there's our CV over M here. And then when you divide by C, it's like the reciprocal, so there's my CV over R here. So I meant CVM over R and CVM over R. So it ends up looking like this. Now I'm just bringing it down here, so I've run out of space. So that's the same thing up here. What I'm going to do now is just take this term that's in the denominator, bring it up by raising it to the negative powers. So we can rearrange the equation to look like this. And now I'm just going to multiply this CV, the molar heat capacity constant volume, to the negative first power times R. I'm going to multiply it by both terms in the other parentheses. It'll simplify down to R over the molar heat capacity constant volume plus 1. Again, I'm just bringing this down because I'm running out of space. The 1, again, can be written as CV over CV over M to find our common denominator. We can add that together, and now what we've done all this work is to convert 1 over C plus 1 into R plus the molar heat capacity constant volume divided by the molar heat capacity constant volume. That was a lot of work, but you're going to see it's actually going to simplify even further. So what we're going to do is reach back even further into focus 1, where we know the relationship between the heat capacity constant pressure minus the heat capacity constant volume is always equal to nR for a perfect gas. All I'm going to do is divide both sides by the number of moles. That can just leave R over here and convert Cp and Cv into their molar equivalents. So now what we're going to do is we can substitute R into this equation we've already derived up here. So now we have an equation for R here. We have an equation up here that has R in it, which is actually the exponent. If we go all the way back, that's up here. So I'm substituting that in. So what we're going to do is substitute R, which is CPM minus CVM, into this. So that's what we see here. This used to be R. So now it becomes CPM minus CVM plus CVM divided by CVM. These two will cancel. This leaves us with the ratio of the heat capacities of CPM over CVM. You could also be CP over V. It also works as well. That's just assuming that we're dealing with one molecule instead of 1 mole. That's the only difference. So by definition, what we do, we finally, after all that work, have simplified that ratio. Sorry, not the ratio. The exponent of 1 over C plus 1 is simplified down to just CPM over CVM. What we can do now is finally bring everything together, right? So there's my new definition of gamma, CPM over CVM. That's for a mole of gas. Like I said, if it's for a single molecule, it's just Cp over Cv. Substitute this back into this equation that we derived above. So there's my 1 over C plus 1. We know over 1 over C plus 1 equals gamma. And now we've cleaned everything up. So all of that work was to clean up our expression where we can finally rearrange it into this final form where the pressure initial times the volume initial raised to the heat capacity ratio equals the pressure final times the volume final also raised to the heat capacity ratio. And this is going to be our equation for the change, the pressure change of a reversible adiabatic expansion of a perfect gas. So what I'll do in the next video is I'm going to, basically what we did in lab is derive what the molar heat capacity ratio is for a perfect gas. I know most of you are pretty solid with this. We had this on the exam. Most people aced this pretty well. What I was noticing is that a lot of people were just making large assumptions where it's almost like not showing a lot of work. So what I would like to do is actually show you how we're going to build this up from basic definitions all the way to calculating the molar heat capacity of the ratio of a perfect gas. So that will be saved for the last video of this adiabatic changes section.